I wanted to show some progress I made on the Blender add-on that I started about 5 years ago and haven't worked on it in like 4 years. But 2 weeks ago, somebody left a comment saying, "Hello, sir, can I make flasher origami?" And I said, "Yeah, no, it can't. And the name origami is still bad because it can't actually make origami." And I'd never heard of the flasher origami, but it's this thing that folds in and rotates, and that would be really cool to make. Um, and so I had a little idea and have tried it out, and it works. It works okay. So to use the updated version, I just have it on the dev branch right now. So make sure you get the file on dev branch, and it does require one little setup step. I could make this automated, but I think it's better if you manually do it. Is to copy paste these lines. We need to install a library called Jax into Blender. So go to the scripting tab, go to the REPL here, copy paste, hit enter. If it wasn't installed, it'll do some stuff. So you should have the Origamify add-on installed. And we're going to start with this water bee base. I don't know if YouTube's going to ban me if I say the full thing. But so this is a base where you have this little square, and these two edges will fold up and in, and these two will fold away. And one thing that's different from the other use of Origamify, which was more of like an unwrapper, is that the face normals, I would say you should just not change or flip, because flipping was used to change which direction the positive angle will rotate. But as I'll probably ramble about a bit later, I think when you have a graph like this, it doesn't really make sense to use face normals, and you really need a per edge data to determine which direction is positive. So just like before, you should have a mesh, have a single object with a mesh, call Origamify. Actually, let's redo that. Select our root face. This will be our root face. And then we're going to call it, and we'll constrain root. And we get this hierarchy, which again, if you hold Alt and tweak the rotation, you can see that positive rotates them all inwards. And you could try flipping the normals, but like I said, in a bigger model, I don't actually think face normals will solve that in a good way for you. So the first thing we're going to do is hit I, insert a keyframe for 0 rotation. And now we're going to advance, let's say, to 50 frames. And we'll just tweak these in a little bit, and then this one goes negative, this one goes negative, and this one goes positive. So this is kind of the starting of the thing. And just what's pretty clear now is why the original Origamify is not actually good at origami shapes, is because it creates this tree hierarchy, which is a spanning tree of the edge graph, where every edge is every edge like this is an edge between the faces, and the spanning tree takes a subset of that graph. And for example, the edge that was here isn't included in that spanning tree, because if it was, then you would have a cycle, and then it wouldn't be a tree, and Blender wouldn't accept it, and like the whole parent-child rotation stuff wouldn't work as before, and everything wouldn't be good. So the thing I've added is a thing called origami snap. Maybe it should be called Origamify snap. I don't know. And origami snap will boom try and line up the vertices, and it has an option to insert keyframes so that it'll do the snap and then insert the keyframes. You should have the root object selected when you call origami snap. So now we're going to advance some more frames and do some more bending, and I'm just being really approximate here. It's not symmetric. I already did that one. And so you can see this is like pretty bad. We select the root again, we call it origami snap, and you can see that it snapped into an asymmetric position, like it's a little wonky. This one is more bent. I don't have a way to do anything about that right now, but you could, I think, manually try and start it out in a pretty symmetric place. But so we'll just keep doing this some more, and we'll call snap, and then we'll go a little further, maybe add one more. And get it kind of close, and then snap, and there you go. That's like pretty good. And we inserted keyframes, and so now if we just shorten this up, we can watch our animation of the base getting folded, and that's pretty cool. But if you look over here at the beginning and kind of in the middle there and right there, the edge isn't constrained at all. It's not going to be perfectly making contact. At the endpoints, they're good, but in the frames in between, they're still not good, which is a bit annoying. See, like right there, it came apart. And so the next thing that I did is, excuse me, add a thing called subdivide, which, okay, this one you need to select the hierarchy and then select the starting keyframe of what you want to subdivide, and it will subdivide this keyframe and this keyframe for all the things. And now we'll call snap subdivide, and I don't know, let's do 5. Yeah, it's going to be a bit laggy because I don't know how to do a better, more prompt thing. Okay, so that's cool. So maybe let's do the same thing here. And just to, if you hit F3 here, it's not going to show it to you. You have to have the mouse over on the thing, on the object viewport or whatever it's called. I don't know. And 5, and it's going to take a sec. It's thinking, I think. I don't know. Do I just hit enter? Did it do it? Yeah, it did it. Okay. And so now it inserted a bunch of keyframes. So now if we watch this back, I mean, it's still gonna not be perfect in between the keyframes, but just by adding more keyframes, it ends up doing pretty good. And so you see it doesn't look great here. So we can just do it one more time. Select hierarchy, select our keyframe, hover over, snap subdivide, 5, and we're good. So now we have like a pretty good little folding animation where the piece of paper actually stays together. Okay, so then the next thing I'll show is on a Mira Ori tessellation, which is like these rhombus. You can just make a grid and then shift some vertices around. And again, I'm just leaving the face normals up, and I'm gonna choose this as the root face to get a X limit rotation constraint so that it won't rotate. And the way this one folds is that it accordions this way and this way. So we just need to alternate positive and negative bends here. And this one can be a little tricky. Let's see, this has got to go up, down, up, down. So let's just see what happens. Hey, that worked. Okay. Sometimes it doesn't work and you kind of gotta tweak it some. But this is really good. So we'll insert keyframes there. I'm gonna select the hierarchy and move it to 50 because we never we didn't insert our original thing. I don't know why that's not working. I think because I need to select it all. But I just did an Alt and then entered it so that we can insert our base rotation, and then you can see that it animates there. So let's try another one of these with a little bit more. Snap. And yeah, see, it's not perfect. It is leaving, so let's see what happens when we snap again. Because it'll use the current position as the starting point, and there we go. So that one looks pretty good. So we could maybe add some keyframes between that. So we can select hierarchy, select this keyframe, call snap subdivide. It's going to think for a bit. And it added some keyframes, and then we can call it again on this one. And we should get some more keyframes. And there we go. We got like a pretty good animation of a fold. So I think that's pretty cool. Okay, so to kind of briefly explain how it works, let's go to a situation again where we cause some separation. So we wanted to kind of increase the fold here. So we have this target fold that is not perfect anymore. And so we have this gap between these vertices that should be touching. If we actually look at the root of the hierarchy, there's a some custom properties stored on it, and one is called correspondence. Another is that every object has the original face index. So here's face 5, face 3, etc. And what this correspondence stores is for every edge that wasn't included in the spanning tree, which there's only one edge that's not in the spanning tree, which is this one right here, which then, kind of gets doubled into 2 edges, but really it corresponded just to 1 edge. This says something like the 0th face, yep, and the 1 face. So these 2 faces gives the 2 face indexes, and then there's 2 vertices per edge. So every edge has 2 vertices. The 2 vertices that should be at the same point, and it's the edge index in each of those objects. So it basically just says that the vertex of this face over here should be the same at the same place as that vertex here, and likewise for this one. In this case, that vertex is always actually going to be the same no matter what bend angle, but in general, you can have both kind of off in space, and you need to try and get them both to line up. And so when you go to call origami snap, we run an optimization procedure using the JAX library. That's why you have to install it. And what that's going to do is the optimization procedure has a bunch of variables that it's going to tweak, and the variables it tweaks are the rotation x of all the nodes in the hierarchy, all the bend angles that it can control, which again, it can't control this bend angle at all. That's like because there's no parent-child edge there. But so for all the ones it can control, it tries to tweak them such that it minimizes the loss, where the loss is the sum of all the squared distances between the vertices that should be the same. So if these vertices are like, far apart, the loss is really big, and if they're close together, the loss is really small. If you start Blender from a terminal, you can see some of the output that it outputs, which is basically the loss after every run of it, and this is all just the whole optimized results. You see it'll like call the function 16 times, blah blah blah. But the nice thing is that it uses AutoGrad to do this, so the code is actually pretty simple, all things considered. Blah blah blah. Yeah. So here's really the whole thing is that we have some bend angles, and then we call this minimize with our objective, and the objective is we apply all the rotations for the hierarchy, and then we can look at the distance between the vertices that should be the same and add them all together, and then JAX will tweak all these angles until they're small. And so there's a bunch of things that this method does not guarantee. Like it could, for instance, like happen to find a state that minimizes the loss, like basically in the completely unfolded version, but it tends to find ones that are close. You could make different objectives that yeah, see, it found one that was close. You could make different objectives that would optimize for like the smallest change from the initial angle, but I haven't done that yet. Okay, so for kind of the next steps that I think could be possible and just don't have the time for right now, is that, for example, if you go to origamisimulator.org, which is a very cool website, and it kind of uses this, elastic model to make things fold, which is really cool, but it's not in Blender, and it's not exact. It has some patterns. Yes, the pattern you can import as like a SVG, and the color of the edge denotes whether it's mountain or valley or border, and the opacity in the SVG determines the target bend angle. So basically for every edge you get a target bend angle. And so if you could import that into Blender and then kind of save that target bend angle per edge, then you should be able to have an objective that would try and find an appropriate bend that was as close to those target bend angles as possible, but also with the least, I don't know what to call it, least gap between the vertices that should be the same.